In this video, you will learn about inverse variation. To begin, let's look at an example that illustrates this concept. Now let's say you're traveling someplace, and you are traveling 60 miles total. Now let's say you were to go 10 miles per hour. If you're going 60 miles at 10 miles per hour, it would take you 6 hours to travel that distance. And that is what you see here in the table, 10 miles per hour. And then over here in the right column, we have the hours that it takes to travel. If you were to go 15 miles per hour, it would take you 4 hours to go 60 miles, because 60 divided by 15 is 4. Okay, if you were to go 20 miles per hour, it would take you 3 hours. 25 miles per hour, it would take you 60 over 25, or 12 over 5 hours, which would be 2 2/5 of an hour. If you were to go 30 miles per hour, it would take you 2 hours to travel the distance of 60 miles. So notice the relationship. If I take the rate times the time, or 10 times 6, I get my miles, which was 60. So rate times time gives me 60. All right, so that is the relationship, and that is an equation that would represent this type of problem. So we see here, if the speed increases, so if you travel faster, the amount of time it takes to go the distance would be lower. It would decrease. So as the speed increases, the time it takes to travel decreases. So we would say the time varies inversely as the speed. So this is called an inverse variation, because as one value increases, the other value decreases. And this number 60 is called your constant of variation, because that is the one thing that stays the same. The rate and the time could change, but we know that the distance is the same, that is 60. So more formally, our definition of inverse variation says that as one value increases, the other value does the opposite, or decreases. Or if the one value decreases, the other value increases. They're both doing different things. They're doing opposite things. So looking back here at this equation, rate times time equals 60. Another way I could maybe think of this is I could rearrange this to solve for t. So if I wanted to, I can divide both sides by r. So if we had r times t equals 60, I could divide both sides by r. Now we have t equals 60 over r. Now this setup is going to be more of what we want as we move forward, because this can be translated as t varies inversely as rate. So the time varies inversely as the rate, and 60 is our constant of variation. Because we're going to need to know how to translate from English into math notation here in a moment. All right, so we said the time varies inversely as the speed. So it's different than directly proportional or direct variation. Because with direct variation, we took the constant times whatever you were working with. Here with inverse variation, we are dividing the constant by something. So that is the difference between a direct and inverse variation as we set up our different equations. So as we said, inversely proportional says as one value increases, the other value decreases, and as one decreases, the other value increases. So in English, if you were given an expression such as y varies inversely as x, y varies inversely as x, this can also be translated as y is inversely proportional to x. So the phrase varies inversely or inversely proportional, those mean the same thing. Now to convert this into math notation, we see the letter y, so we write the letter y equals, and then we have our constant, which is going to be the letter k, and like we said in the previous slide, with inverse variation, instead of multiplying like we do with direct variation, we will divide the constant by something, And in this case, we're dividing by x because it's inversely proportional to x. So my equation would look like y equals k divided by x, where k is the constant of variation. That is some number. We'll work with this a little more later in the lesson with converting into math notation and then solving. But for now, let's take a moment and look at what this would look like if you were to graph. Because the graphs of inverse variations looks unique. It's different than what we've dealt with up to this point. For example, if we had y equals 1 over x. This is inverse variation, where 1 is your constant of variation. And if you were to graph this, we can plug in different values for x and figure out what we get for y. So here we see a table with some x values plugged in, and here is a column with what we get back out for y. So if you plug like -4 in for x, we'd have -1/4 for y. Plug a -2 in, we have -1/2. Plug a -1 in, we have 1 over -1, which is -1. And we have fractions we could put in there. So if x is -1/2, then y would be -2, because 1 divided by -1/2 is the same thing as multiplying by the reciprocal. So 1 times 2 over 1, and that's negative. So that's going to be -2. Anyways, we could plug in all these points and get those values back out for y. And then here, if we plug in some positive values for x, we get positive values for y. All right, so if you want to pause and take a closer look at this table, feel free. But just note that we can graph each of these points. By the way, note that x cannot equal 0, because 1 divided by 0 is undefined, right? If the 0 is underneath, it is undefined. So if you were to graph all of these points, notice what we get on the graph. We're going to get this weird shape like this. All right, so these are all the points that we have in the table. So this graph has a special name given to it. And this graph is called a hyperbola. All right, so anything that looks like this is a hyperbola. Now let's take a moment and compare graphs. So if we had y equals 1 over x, we have this graph as we just showed. Now what if you had a -1 over x? What you would get is the hyperbola is flipped. So instead of being in the first and the third quadrant, the top right and bottom left, now it's in the second and fourth quadrant, in the top left and bottom right. All right, so it's still a hyperbola, it just moved over to different parts of the graph. So the graphing part of this was just kind of a side note, something kind of interest. And now we're going to get back to the formulas, like converting from English into math notation, and then also how to use that to solve equations. So here we are told z varies inversely as h. Our objective at this point is simply to convert from English into math, and then at the end we'll use that to solve. So converting this into math notation, we take the z, and it's going to be equals to k, and then inversely means we divide. So varies inversely, we divide by this h. So z equals k divided by h. Next we have m varies inversely as a. So here we have the letter m, so write m, and then equals varies inversely means we take k divided by something, and this will be divided by the letter a. So my equation would be m equals k divided by a. Another example, we have x varies inversely as both y and z. So this one is different because we have it varying inversely as two different variables. But my setup will be the same. We have x, so we write the letter x. Varies inversely means we have equals k divided by something. Well, k divided by what? Well, k divided by y and z. So y times z in the bottom. So that would be my equation. If we had A varies inversely as B and C, we would have A, and then varies inversely would be equal to K divided by something. So varies inversely as B and C, so we have B times C in the bottom. So that would be my setup. So again, if it is directly proportional, you'd have K times something, and if it's inversely proportional, we have K divided by something. So combining both the concepts of direct and inverse proportionality, we have an example here, where x varies directly as y and inversely as z. So in the same problem, we have two things, two different variables, one of which is directly proportional, the other of which is inversely proportional. So when I set this up, I need to remember that directly means multiply and inversely means divide. So I have x, let's write the letter x, varies directly, would be equal to k times something. Directly means multiply. So directly as what? Well, directly as y. So I multiply by y. And inversely as z. Inversely, think divide. So we take this and divide by the letter z. So my equation that would be represented by this English expression would be x equals k times y over z. One more example like this. We have A varies inversely as B and directly as C. This one you need to be a little careful with. So here we have A, write the letter A, varies inversely. That'd be k divided by something. So k divided by what? Well, k divided by b. Now the part to be careful with is this part right here, directly as c. So remember, directly means multiply, right? It's multiplying by c. So when you multiply, remember we're multiplying k by that value. So k we multiply by c. So the c would go on the top. All right, so it's not in the bottom with the b. All right, it's going to go on the top with the c. If it's in the bottom, that would be dividing, like k divided by c, which would be inversely. So my setup would be A equals k times c divided by b. Now let's take a moment and explain how to use these different setups to solve for an unknown value. Here it says z is inversely proportional to r, and z is 32 when r is 2.5. Find r when z is equal to 8. So to begin, I always want to set up my equation, and here we're going to look at the phrase z is inversely proportional to r. The equation for this would be z equals k divided by this value r. So z equals k divided by r. Once I have that equation, I'm going to use this scenario 1 right here to calculate what is my constant. And then from there I can use that constant and this part here where it says z is equal to 8. We can use those two things to find r. So let's look at scenario 1. We plug in a 32 for z and a 2.5 for r. So we have 32 equals k divided by 2.5. Now to solve, I need to get rid of the 2.5 in the bottom and do that by multiplying both sides by 2.5. The 2.5s will cancel. I have k on the right, and on the left, 2.5 times 32 would give me 80. So I have k equals 80. So from here, I can use the k value, and I can use the fact that z is 8, and plug that into my equation again to solve for r. So here I have 8 for z, so 8 equals 80 divided by r. Now from here we need to solve for r. And there's different ways you can think through this, because this is a little different where r is in the bottom. So bottom line, I need to get rid of the r in the bottom. So one way I can think of this is to get it out of the bottom, I can multiply both sides by r. Because when I do that on this right side, when I multiply, the r's will divide out. I'm left with 80 equals 8 times r. And then I can divide both sides by 8, and r would equal 80 over 8, which would equal 10. So that is one way I could have solved that. The other way is I can think of this as cross multiplication, where I can multiply cross 8 times r equals 1 times 80, which is 80. And then I can divide to get r equals 10. So either way, we get the same answer. And with practice, if you can do this in your head, you can simply just switch the 8 and the r. So if you can do that shortcut, that would work as well. R equals 80 over 8, which would equal 10. Alright, so actually 3 ways you can think of this problem. Next example, we have p varies inversely as the square root of q. And p is 10 when q is 36. Find p when q is equal to 16. So to begin, I want to set up my equation. So p varies inversely as the square root of q. So we have p varies inversely would be equals k divided by something. Well, k divided by what? Well, it's k divided by the square root of q. So the square root of the letter q. And we see that typed right here. P equals k divided by the square root of q. So from here, I look at scenario 1, where it says p is equal to 10 when q is 36. I plug 10 and 36 in for p and q. So 10 equals k divided by the square root of 36. So I can use this to find k. The square root of 36 is 6. And then from here I can multiply both sides by 6. The 6's will cancel. I have k equals 6 times 10, which is 60. Now I'm not finished yet because my goal is to use that to find p when q is 16. So I need to use the equation one more time. P equals k divided by the square root of q. I plug a 60 in for k, and then a 16 in for q to solve for p. So p equals 60 divided by the square root of 16. The square root of 16 is 4, so 60 divided by 4, that gives me 15. So my solution is 15. One more example. We are combining the directly proportional with inversely proportional. And this problem says that suppose that r varies directly as p and inversely as q squared. And that r is 21 when p is 3 and q is 2. And find r when p is 2 and q is 3. So to begin, I want to set up my equation. So r varies directly as p. That would be r equals k, and then directly would be multiplied. So k times p. Okay, and is inversely as q squared. Inversely means divide. So I divide this by q squared. So that is my equation. R equals k times p divided by q squared. And then from here, I need to look at scenario 1, which is right here, and plug in these numbers to find k. So plug a 21 in for r, plug a 3 in for p, and a 2 in for q. When I do that, I'm going to have 4 on the bottom. So I have 21 equals 3k over 4. And then I can get rid of the 4 by multiplying both sides by 4. So 4's will divide out. I have 3k equals, that's 84. And then from here I can divide both sides by 3. So I'm going to have k equals 84 over 3, which is going to give me 2 and an 8. So k would equal 28. So k is 28, and we can now use this along with information from scenario 2 right here to find r. So I need to use the equation one more time. R equals kp divided by q squared. So for k, I plug a 28 in. For p, I put a 2, and for q, I put a 3. So I have 28 times 2 divided by 3 squared, which is 9 for the bottom. Well, 28 times 2 is 56. So I have 56 divided by 9, which you could divide and get 6 with the remainder of 2. So I can write that as 6 and 2 nines. So my answer is r equals 6 and 2 nines. And that concludes our lesson for today. We will see you next time.